Good morning, students. So today we are going to start our 8th unit, D and F block elements. Okay, so in this unit we are going to study about the electronic configuration of D block elements and few physical properties of transition metals. Okay, so first of all, let us start with D block. Okay, now see, where is D block in our periodic table? D block is between S and P blocks of the periodic table. Okay, now how many series are there in D block element? In D block there are 4 series: 3D series, 4D series, 5D series and 6D series. Okay, so those particular elements for which atomic numbers are from 21 to 30, the elements are from scandium to zinc, they are in the 3D series. Similarly, the elements from yttrium till cadmium, they are in the 4D series. From lutetium to mercury, they are in the 5D series, and similarly from actinium to copernicium, okay, they are in the 6D series. Okay, now see, when we study about the properties, then we will mostly discuss the properties by taking 3D, 4D and 5D series. Okay, so these we are going to discuss in detail. Now first of all, what about the electronic configuration? Now see, uh, for 3D series, the atomic numbers are from 21 to 30 and the elements are from scandium to zinc. Okay, now see, in the valence shell there are two orbitals, one is 3D and other is 4s. Okay, so for scandium there is presence of one electron in 3D and two electrons in 4s. So 4s will be filled first and then 3D is to be filled. It is according to Aufbau principle. So 4s is to be filled first and then whatever electrons are left out, they will be filled in 3D. So as we discussed earlier, in case of copper and chromium, there is exceptional electronic configuration as expected from the Aufbau principle. There is some change. So in both the cases, there is presence of one electron in 4s orbital and 5 electrons in 3D for chromium and 10 electrons in 3D for copper. Okay, so this is what the anomalous behavior is, because by doing this, what happens, they occupy most stable electronic configuration, so they exist like this. Okay, now what about electronic configuration? Means, what is valence shell electronic configuration? So valence shell electronic configuration for D block elements is n-1d 1 to 10, ns 1 or 2. Okay, so here we are going to discuss one more thing. Sometimes we are asked that what do you mean by transition metals? So one of the feature of transition metals is that there must be presence of unpaired electron in d orbital. If there is presence of unpaired electron in d orbital, then we will say it is transition metal or it is transition element. Okay, now when we talk about these elements, zinc, cadmium, mercury and copernicium, then what happens? These elements belong to the 12th group, that is last group of the D block, and in this particular group the valence shell electronic configuration is n-1d 10, means there are 10 electrons in d orbital and there are 2 electrons in s orbital, means these are fully filled orbitals. All the orbitals are fully filled. So since they do not lie in this definition, what is the definition? That there must be presence of unpaired electron in d orbital. So in all these four cases, there is absence of there is absence of unpaired electron in d orbital. So they are also not regarded as transition metals. So sometime we are asked that why they are not regarded as transition metals. So we will say that they are having fully filled valence shell, so they are not regarded as transition metals. Okay, now see here we have taken one example. Sometimes we are asked question like this, that scandium is a transition element but zinc is not a transition element. Why? So here what reason we have given? We have given the reason that in case of scandium, when we write the electronic configuration, then there is presence of one unpaired electron in 3d orbital. So it is regarded as transition metal. But in case of zinc, there is fully filled d orbital. There is absence of valence unpaired electron, so it is not regarded as transition metal. Okay, so this is one of the question. Now let us discuss the physical properties. First of all, we are going to discuss about melting and boiling points. Okay, so in general when we talk, then transition metals have very high values of melting and boiling points. Okay, and they are very hard and have low volatility except these three. So these three are those elements which are at the last group of the D block elements. Okay, so here one more question comes, that zinc, cadmium and mercury are soft metals. Why? Okay, so what we will say, zinc, cadmium and mercury do not contain any unpaired electron, so they cannot form bonds properly. So metallic bond formation does not exist in these cases, and so they have very low enthalpies of atomization, and so they have low values of melting and boiling points, and so they are soft metals. Okay, this way we can say it. Now let us look at the graph. Okay, now see, this one is for 3D series, this is for 4D series, this is for 5D series. Now what we are able to see here, first of all we can see that melting point values of 3D series are lowest as compared to 3D, 4D and 5D series. Okay, here the values are starting from here, and for 4D they start from here, for 5D they start from here. So very first thing is that when we move from 3D to other series, then there is increase in melting and boiling point values. Okay, one thing is this. Second thing, when we look at the trends of values, then what we find that in the beginning they keep on increasing, they reach a maximum value, and then again they start decreasing. Okay, so this is in accordance with the enthalpies of atomization values. The way we are getting our graph here, similar graph is obtained if we plot the graph for enthalpies of atomization values for these elements. So it means that melting and boiling point values directly depend upon enthalpies of atomization. What do we mean by enthalpies of atomization? Enthalpies of atomization means the amount of heat change during the conversion of a particular crystal lattice into its atomic form. Okay, that is called enthalpy of atomization. Now this thing, what enthalpy of atomization? Enthalpy of atomization depends on the type of bond formed, how strong the bond is. On the basis of that, the enthalpy of atomization value will be depending upon. Okay, so now on what factor this metallic bond formation depends? Metallic bond formation depends on the number of unpaired electrons present in the elements. In case there are more unpaired electrons, then there will be more stronger bond formation. Okay, so if there is more stronger bond, then more energy will be required for breaking that particular lattice into atoms. Okay, So that will have higher enthalpy of atomization value. Now when we start moving from starting to the end of the series, then what we find? We find that there is increase in the number of unpaired electrons. Then the unpaired electrons reach to the maximum value, and after reaching the maximum value, the number of unpaired electrons starts decreasing. So in the similar manner, we find that the metallic bond strength that starts increasing in the beginning, metallic bond strength reaches the maximum value, and then it again starts decreasing. Okay, so in the same way, enthalpy of atomization values also change. Okay, so now see, in this diagram we can see this is for 3D series, this is for 4D series, this is for 5D series. Now see, these are the enthalpy of atomization value graph. So here we can see that in the beginning value starts increasing, reaches the maximum value, then again starts decreasing, and then this is the way how we find it. Okay, so why this type of graph is obtained? This type of graph is obtained because the number of unpaired electrons start increasing from the beginning, it reaches the maximum value, then again it starts decreasing. Okay, so what result we can say? We can say that greater is the number of valence electrons, stronger is the resultant bonding. Now here what do we mean by saying this? We mean that number of unpaired electrons. Okay, so this is what we can say on the basis of melting and boiling point values. Now let us come to atomic and ionic sizes. So atomic size or ionic size, this is one and the same thing. Okay, now see, in general what we say that when we start moving from left to right, then what do we observe? We observe decrease in radius with increasing atomic number. Okay, this is in general we obtain like this. Okay, now in this case there is addition of electron in the d orbital. Okay, so when we start moving from left to right, then what happens? Electrons are added in d orbital, and the shielding effect of d orbital is not so effective. Okay, so net electrostatic attraction between the nuclear charge and the outermost electrons increases. So what happens when electrons are being added in the d orbital? Then what happens? There is lesser shielding effect. Because of lesser shielding effect, the effect of nucleus on the outermost electrons is more, and because of that the atomic and ionic radii decreases. Okay, now within a series, now when we talk about a particular series, let us suppose first series is also called 3D series. They are called 3D, 4D, 5D, 6D because the last electron enters in 3D orbital. In case of first series, it enters in 4D orbital. In case of second series, it enters in 5D orbital in case of third transition series, and the last electron enters in 6D orbital in case of fourth transition series. So they are also known as 3D, 4D, 5D or 6D series. Okay, now when we talk about the series, then variation in the size that is very small. Okay, now how it is, that we are going to discuss in the next curve. Okay, now we are going to compare 3D, 4D and 5D series, and on the basis of that we will be discussing it. Okay, now see, whenever we start moving in a series from left to right, then three type of changes we can observe. There is no regularity in the atomics and ionic size change. Three things that we can observe: at the beginning of the series we can observe, in the middle of the series we can observe, and at the end of the series we can observe. Okay, now let us discuss first in the beginning of the series. Okay, so in the beginning of the series what happens? Atomic number increases. Okay, effective nuclear charge also increases. So electron cloud, they are pulled close to the nucleus because the effect of added electron is less than the effect of increased nuclear charge. So what is the result? Result is atomic size decreases. Okay, so what we have found, in the beginning of the series there is decrease in the size. Now when we come in the middle of the series, then what happens? Now see, we are what we are saying, that there is addition of electron in the d orbital. So when we move in the middle of the series, then there are more electrons in the inner 3d orbital when we talk about the first series. Now inner 3d electrons, they shield the outer 4s electrons effectively. Okay, now effective nuclear charge experienced by 4s electrons increases. Okay, and it increases very slowly. So what we are going to say here, that when the number of electrons increases in 3d shell, then what happens? Then the effective nuclear charge which is being experienced by 4s electrons, that increases, but the increase is little less. Why? Because number of electrons have been increased. Okay, what happens? The inner electrons, they act as a screen or shield. So when the number is less, then they are not so strong shield. When the number is more, then they will be showing greater effect than that. Okay, so the overall result is that there is slow decrease in the atomic radius. Okay, slow decrease in the atomic radius. What does it mean? It means that when we move in the middle of the series, then there is decrease, but it is quite less, and we can also say that it remains almost same. The size remains almost same. Okay, now when we talk about end of the series, then what happens? Now when we arrive at the end of the series, then the total number of valence electrons, that increases to the maximum. Now because of more electrons, what do we feel? We feel too many repulsive forces between the electrons. So inter-electronic repulsive forces, they become too much. Because of that repulsive force, at the end of the series we observe increase in the atomic size. Okay, so now what we have observed? We observed that in the beginning of the series there is decrease in the atomic and ionic radius. In the middle of the series the size remains almost constant, and at the end of the series size again increases. Okay, now see here from the graph, you can see here, this is green one is for first series, blue one is for second series, and this one is for third series. Okay, so now from this graph what we can say? See, we started from here, then what happened? The size started decreasing. Okay, now in the middle of the series, when we arrive at this particular point, then you can see there is not too much decrease or increase. Okay, the values are almost same, there is very less effect. Okay, but at the end of the series if we see, then these values are increasing. Okay, so these values are increasing. Why they are increasing? Because of more inter-electronic repulsive forces. Okay, now here one more phenomena you can see. See here, when we talk about these two series, now what we can say here? Here what we are able to see, in this case we are able to see one thing, that the sizes of 4D and 5D series elements, they are not showing too much difference. Their ionic radii are almost same. There is very less difference in their sizes, so we can also say that they are almost same. Now why the size of 4D and 5D series is same? Now here one more phenomena comes, that is called lengthenoid contraction. Now what is lengthenoid contraction? Okay, now see, look at this. This is our 5D series. Now what happens in 5D series? When we are moving from 3D to 4D, then there is increase in size. But when we are moving from 4D to 5D, then there is almost same size. So why is it so? Now see, after lanthanum, there are 14 elements. Here there are 14 elements, and those 14 elements belong to inner transition series and are called lanthanoids. In case of lanthanoids, the last electron enters in 4f orbital. So when we come to hafnium, then what we get? We get a fully filled f orbital. Okay, there is 4f orbital which is fully filled. So because of this, what happens? The screening effect of f electrons is minimum. So because of this minimum screening effect orbital, which is fully filled and is available for all these elements, see, all these elements will be having fully filled 4f orbital. So what will be the effect? The effect of nucleus on these all elements, it will be more. So because of more effect, its size will decrease. Okay, so what happens? Ultimately, sizes of all these elements, they become almost same as the sizes of 4D series elements. So this phenomena is called lanthanoid contraction. Okay, this we are going to discuss separately ahead. Okay, now next property is ionization enthalpy. Now see, in case of ionization enthalpy, we know that it is the energy required to remove an electron from its outermost orbital in its isolated gaseous state. Now, if we compare the first ionization enthalpies of the d block elements, then they are greater than that of for s block elements. Why? Because the d block atoms, they are smaller in size. Okay, and because of smaller in size, there is effective nuclear charge value more. So because of more effective nuclear charge, in general, first ionization enthalpy values for d block elements are higher than that of s block. Okay, now when we move in a transition series from left to right, then what happens? The nuclear charge of the elements increases. Okay, nuclear charge increases, and there is addition of electrons in the 3D subshell. If we are talking about first transition series, in case of second there will be 4D, and in third there will be 5D. Okay, so two things which we know, that when we are moving from left to right, then what happens? The nuclear charge increases and there is addition of electron in the 3D shell. Okay, now screening effect of 3D electrons is significant. Okay, now the effective nuclear charge experienced by the 4s electrons increases very slightly. Okay, so what does it mean? It means that the nucleus or effective nuclear charge on the outermost electrons, that will be more, but that will be increasing very slightly. Okay, that will be more, but it will not be too much. Okay, why? Because the number of electrons have increased to large number in case of 3D, and because of more number of electrons, the screening effect has become significant. Means if there is less number of electron, presence of less electrons, then the screening effect is very low. Okay, they cannot act as a good screen. But if there are so many electrons in 3D orbital, then they will act as a proper screen, and they will have proper screening effect. Okay, now this is the reason that when we look about second, third and fourth ionization enthalpy values, they are also increasing. In general, what we say, the successive ionization enthalpy values are higher. Here also they are higher, but the increase is not too much. It is increases there, but the value is not too much. Okay, so these are the things for ionization enthalpy. Now let us discuss about the last property in this session, that is oxidation state. Now see, One question is asked many times, that why do transition elements show variable oxidation states? Okay, variable oxidation state means they can exist in so many oxidation states. Okay, so why? Now if we talk about their valence shell, then that valence shell involves these two orbitals, 3d orbital and 4s orbital, when we talk about first series. Okay, now if we compare their energies, then their energies are not very much different. Okay, there is less difference in energies. Okay, and they are available for bonding, means both the orbitals, they are available for bonding. Now elements of first transition series, they form ions of roughly the same stability by losing different numbers of the 3d and 4s electrons. Now what do we mean by this? We mean to say that when we talk about first transition series elements, then from 3d and 4s orbitals there is loss of electrons, and they can lose electrons in different numbers, so they can show so many oxidation state values. Okay, now let us see this chart. If we see this chart, then we can say manganese shows the maximum number of oxidation states. Okay, now why do we say that this is like that? This is because with the increase in number of unpaired electrons, the tendency to show oxidation states, that increases. Okay, now see, if you look at this, scandium can show only one oxidation state, that is +3. Zinc can show only one oxidation state, that is +2. Now why is it so? Because in this case the number of valence electrons are only 3, and in this case they are fully filled, so they can lose only 2 electrons, so that the form which it acquires, that is again stable. Okay, so this is the trend, that how we can see the different oxidation states of all the transitions elements. Okay, so this is because of the involvement of both the electrons available in n-1d and ns orbitals. Okay, now let us discuss what we said. Very first thing, scandium and zinc do not show variable oxidation states. So sometime it is asked that which oxidation state is shown by scandium. So what do you have to say? That only +3 oxidation state is shown by scandium. Why? Because by doing so it acquires the noble gas configuration of argon. Similarly, zinc can also not show variable oxidation state. It can only show +2 oxidation state, because by doing so it also acquires nearest noble gas configuration. Okay, now second point, all elements of the first transition series can show oxidation state of +2. Now see, scandium cannot show, so except scandium all elements can show +2 oxidation state. Okay, similarly all elements can show +3 oxidation state, and the exception in this case is zinc. It can only show +2 oxidation state. Okay, one more thing, manganese, it can show +7 oxidation state, but it is shown only in the combined state, just like in this ion or in this molecule. Okay, but if we talk about this, then single Mn7 positive ion will not exist. It can show oxidation state only in its combined state. Okay, this type of ion does not exist. Okay, so these were the four physical properties of d block elements. Now this is the homework which you have to complete on the basis of what we have studied. Okay, thank you.